Hey, hi, welcome everyone to this session. So let us continue our discussion on basis for topological spaces. Today we are going to learn about something called local basis or neighborhood basis. So before that, let us begin with a quick review of last two sessions. Basically what we have learned, let me quickly recall it. So number one, what we have seen, given a topological space, say x tau, what we have learned? The definition of basis. We say script B contained in tau is a basis for tau or the topological space x tau if what happens guys? Every member of tau, or in other words, every open set can be expressed as union of members of script B. Not all members, maybe some members, right? This is what we have done. First of all, how we have defined basis, right? And then there was, some equivalent condition, how to check something is a basis. And another thing what we have done is, so given a set and say x and some script b contained in 2 to the power x such that this script b has two beautiful properties. Number one, for any x in x, there exists a member, say b suffix x of the script b such that what happened? X belongs to b suffix x. Right. What was the another property? Another property was, say, for any, so for any b1 comma b2 in script b and any point in intersection, there exists a third member b3 in script b such that x belongs to b3 which is sitting inside the intersection of b1 and b2, right? Such kind of collections we have considered. And what was our claim? The claim was then script b will be basis for some topology, say tau on x, given by what was that some topology? How we have described this? All subsets of x such that if you take any point in U, okay? So for any x in U, there should be a member of what script B such that x belongs to B suffix x which is contained in U. So collection of all such all such sets will form a topology, right? Let me have a remark here. Let me have few remarks. And of course, we have seen one or two examples. Don't worry, we will look into more examples. But first, I will develop some theory, then I will move on to those examples. Okay, so first thing I want to tell you guys is clearly, by definition, every set in basis is also open, right? That is what we have, seen because it is in definition. So, what we call such sets, so we call such sets to be basic open set. What we call them? Basic open set. Basically, a set which is open and lies in a basis is called basic open set. Number two, I want you to observe one thing. So let us say X tau be a topological space. Space with basis, say script B. Okay? What is my claim? The claim is then tau is nothing but tau bracket script B. I hope you remember this notation. Recall some set A, say, is basically the smallest topology on X containing A. You also write in short topology on X generated by this set A, right? I hope you remember this. We have done this in, very beginning when we have proved the things like that. Intersection of topologies would be topology and all things similar to that. And I have told you this concept is gonna be very useful in future. At that time, you can revisit the lectures if you haven't seen them or if you've forgotten them. Okay, so let us see why. So what is the claim here? The claim is tau would be the smallest topology which contains script B, right? So let us have some other topology. Okay, so let tau prime be any other topology on X, of course, such that the script B is contained in tau prime. Okay, now what we have to show? The claim is tau is contained in tau prime. Let us see why. So let us take any open set. Let U belongs to tau. What it means, guys? U is equals to union B in script lambda B for some script lambda contained inside B. Why? Because B is a basis for tau. Basis of tau or X along with tau. Like I told you, one and the same thing. We can use both. Okay, it says the way of saying. Okay, now note that this B belongs to tau prime for every B in capital lambda. Why? Because the script B is sitting inside where? Tau prime. That's what our hypothesis is. Right. And what is tau prime? And tau prime is a topology. So it is closed under arbitrary unions. So this implies U belongs to tau prime. So you see, this is very easy to observe that tau is sitting inside tau prime. So tau is indeed what? The smallest topology which contain the set script B, right? I hope you understood this. So sometimes you also use the terminology topology generated by this basis, by some basis. Okay, so I hope this is clear. Now, let me let me give you one more remark. Like I said you that this basis, if you know the basis, you know about the topology, right? That is what I have begin with, that it is analogous to vector spaces, right? So let me give you one example in uh, in the same line. So let us have one. So let X be a set and say tau 1 and tau 2 be two topologies on X such that, let us assume one thing, tau 1 is contained in tau. Okay? Moreover, you know something more. Moreover, assume B1, okay, Bi is a basis of tau I or for tau I, because now you know the meaning of the two concepts which I have defined in last two sessions. So it's fine if you use for or of. So tau I, of course, for all I from 1 to. Okay, let us assume these are, we know about the basis. Now, like I told you, bases are gonna, you know, reduce our work like in vector spaces. You work with the bases there and you work with the vector spaces. Similarly, you work with the bases here and you can talk about topologies. So let me come to the statement step by step. So let us take, this is grid B. Sorry. Let us take some member of B1. Okay. So let B1 belongs to grid B1 and X belongs to B1, Bn point. So this is also arbitrary member I am taking from script B1 and some point in script B1. Okay. Now, tau 1 is sitting inside tau 2 and script B1 is contained in tau 1 implies what? Script B1 is also sitting inside tau 2, right? Okay. So what this implies? This set B1 also belongs to tau 2 and script B2 is a basis for tau 2, right? So what you will get here? What you will get by the definition of basis? I hope you remember the equivalent definition of basis. So you have a set, you have an open set and a point in that open set, X. What will happen? So there exists B2, B2 in script B2 such that X belongs to B1, X belongs to B2, which is sitting inside B1. Is it right? I hope this is very clear to you guys. So what we get here is, let me have like a statement. So observation. So this leads us to following result. So let me have it. What we have observed above. So let me just write, the conclusion. So let X be a set and tau 1 and tau 2 be two topologies on X with B1, script B1 and script B2 be their bases respectively. Now, what this result or theorem tells us, if you want to compare the two topologies, just see what is happening at a basis level. If you want to study the open sets, just study the basic open sets. How? So tau1 is contained in tau2 if and only if for every u in tau1 and okay, so not u in tau1 where I started with, okay, a member of script b1. So sorry, yeah. So for every u in script b1, or you can say b1, let's follow the same notations. So for every member of b1 and for any point in this, or for every point in this x in b1, there exists what? There will be a member in script b2 such that what you have, x belongs to b2, which is further contained in b1. That is what you have. But if you remember, I just have shown one direction, right? So let us prove this result completely. Proof. We have shown above. You see, that's how you do mathematics many a times. You observe something and you check if the converse is true. So here I am telling you it is, yes, it is true. So let us prove this direction, okay? So let's assume this statement holds. So what you have to show. So let's assume this statement hold, and we have to show tau1 is contained in tau2. So begin with a open set in tau1, right? So let u belongs to tau1. Okay, what this implies. So and we know that and b1 is what? Is a basis of what? Tau1. Basically, somehow I have to use the statement for every basic open set in tau1. So b1 member. So somehow I have to go to b1. That's what I'm trying to do. So I have taken an open set, okay, and arbitrary open set and some member of tau1. So using that, I will have for every x in u, there exists something, right? Some member of what? b1. There exists b1, say x, because it depends upon x, in script b1 such that what will happen? X belongs to b1x, which is contained in where, guys? U. That is by definition of basis, the equivalent definition of basis, right? From the equivalent definition of basis. I forgot which lecture. The lecture, I think, which session? The last one was maybe 12th, yeah, 11th session, yeah. Equivalent definition of basis. Okay, so now see, you have a b1x in b1 and a point in it. So there exists, this implies by hypothesis, there exists some b2, right? Of course, b2 also depend upon the point x in script b2 such that what will happen, guys? This thing will happen. X is in b2, x, this is in B1x, and where is B1x? B1x is inside U, right? So what we have finally, if we collect the things together, we have for any x in U, there exists B2x in script B2 such that what will happen? X belongs to B2x, which is sitting inside U. So what it means? You take the union over all side. This we have done many times, right? So this would be union x in U, B2x. And this is basically U only. And this is what? This is also U. So what you have? This implies U can be expressed as, you know, union of members of script B2, right? This B2x belongs to script B2 for every x in U. So what you have? You have these B2s are in B2, which is contained in tau2. So you see, U belongs to tau2 because tau2 is of course a topology. So where you started with? You started with tau1 and finally you have this U in tau2. This implies tau1 is contained in tau2. So we are done. So you see the advantage of basis or to know basic open set is it reduces our work, right? A basis might have, less number of elements than topology, right? So that's why this concept is very important. The same sort of analogous important like we have in where vector spaces or if you know groups, modules, the every algebraic structure, you see, you have some kind of concept like basis. Okay, good. I hope this is clear. So I want to give you one what homework. So this was remark 3. So let us have the fourth one. Please try this. What you have to try. So okay. So of course you have a topological space extra. I am not repeating it. Okay, no, let us repeat. So let X tau be a topological space with basis. You know now the meaning of basis tau. Then for A sitting inside X, X belongs to A closure if and only if for every, you know, basic open set. Oh, with a basis, I have by mistake written tau only here. So let's have with a basis script B. So for every U in script B such that X belongs to U, what you should have? U intersection A should be non-empty. See, our work is reduced, right? Rather than checking all for all open sets, it is just sufficient to check what? It is sufficient to check for the basic open sets. So if something is true for basic open sets, it is gonna true for all open sets. Okay. So final remark. I don't think so. I need to write it. So I hope at least little bit about the motivation which I have given you. I have completely justified now that why this is and this basis is also analogous to the concept of basis in vector space. All concepts of basis in Wherever you study in mathematics, all are analogous. All the idea behind all is actually, one and the same. Okay, very nice. So now let me proceed to a very beautiful concept. So NBD means neighborhood. I guess you guys remember it. NBD basis, neighborhood basis, or what you call it, local basis. You might have studied, you right? Maxima, local maxima, minima, local minima, these kind of concepts, if I am not wrong. You have done that, right? So similarly, there is a concept like, neighborhood. Okay, in topology. So whenever you are going at neighborhood level, you will say local. So you will have a concept in topology and you will also study like what is local. So if you have basis, what is local basis? Like for example, in future we will be studying about something called connectedness. Then you will say like, okay, what is local connectedness? So these kind of logics are there. So let me first define, okay, what is this concept? So let X tau be a topological space. And let us take a point in X, okay? Then a collection, a collection script Bx, okay, of subsets of X, of course, some subsets of X, okay, is called a neighborhood basis for X in X. So whenever in topology, from the whole space, you are talking about some concept around a point, that concept you call local. So what is a neighborhood or local basis? So neighborhood basis for X in X if or local basis, okay? So when you call that, let me define like this. Number one, X belongs to B for every B in script Bx. Number two, number two, every member, every member of this, uh, script Bx is a neighborhood of X. So B belongs to n suffix x. Remember, n suffix x is collection of all neighborhoods of the point X in some topological space. Okay. So belongs to this for every B in script Bx. So recall n suffix x is collection of all neighborhoods of X in X tau, whatever the topological space you have. Okay, third thing, and a very important thing, let me write it carefully. For every u in nx, so if you take any neighborhood of x, there should be a member in this b suffix x. Of course, it depends upon you. There should be a member in this b suffix x such that, can you guess? You may stop the video and think for a moment. So I hope you can get it. So let me just write now. such that U is contained in B suffix U. You see, something like basis. Now, is it clear? So it should have three properties. A collection would be a local basis for a point x in X if it has three properties. First of all, every set should contain X. Second, every set in this Bx should be a neighborhood of X. Third, if you take any other neighborhood that should be inside one of the member of this collection or set B suffix X. I hope the definition is clear. Now, let me tell you why such a collection is named neighborhood basis or local basis. I have already given you justification why this word is used, neighborhood or local. Like I tell you, whenever you have a concept for general topological space and you are talking about something similar around a point, then you are calling it local. Okay? Or in this case, neighborhood also. We are using this terminology. And also you are using this neighborhood word because you see, every member of Bx is a neighborhood of X. That's why. Okay. So in terminology, the word neighborhood and local is used. I have justified verbally. I'm not writing it down, but I have said. Now, why the term has basis? So basically, I'm just giving you, the meaning of this terminology. So let us understand that carefully. Okay? Very carefully. So let X star be a topological space. And let us take some neighborhood basis. Bx is a neighborhood basis for X in X. For every X, okay? So for every X, let us take a neighborhood basis, okay? Now, let me tell you, by the way, these neighborhood bases always exist. You can just take Bx to be singleton capital X. Everything works, right? I mean, let us have a remark here. Remark. For any X in X, there exists at least one neighborhood basis. What is that neighborhood basis? Say B suffix X to be okay, singleton capital X. So it will satisfy all property. X is in capital X. Capital X is a neighborhood. If you take any other neighborhood, it would be sitting inside, of course, capital X, right? So that's why we can choose, you know, our neighborhood basis around the point X. Okay, let me continue. Define script B to be script B, collection of all, or you can say, let us write like this. Union all these grid bx, x in x. So basically, I'm collecting all these subsets. What subsets? Which lie in neighborhood basis bx. Okay. What is my claim? Grid B is a basis for tau. Okay. So it would be the basis for this topology, the topological space we have started with. So let me just justify it. So let U belongs to tau be arbitrary and X in U be any set. Okay. Now what this implies? X is in U. U is open in X. So this implies U belongs to neighborhood of X and Bx is a neighborhood of basis. U belongs to collection of all neighborhoods of X and Bx is a neighborhood basis. So what it implies, guys, there should be some member. So this implies there exists Bx in script B, or just take B in script Bx such that X belongs to where? U, of course, and what you have? Let us go above, see the definition. What you have, this U should be inside, you know, this what you call some this B. We have taken here B. Or just a minute. Just a minute, guys. I think I have written something wrong. Yeah, let me correct this. So this is B suffix U sitting inside U. So every neighborhood should contain a member of this B suffix X. That is the third condition. I'm sorry. How I know that I have made this mistake? Because you see, um, I know what I have to do ultimately, like what kind of concept I am defining. So sometimes it will come, it will come by maturity. So this is B, X in B, and this is sitting inside U. So this is happening for, this thing is happening for, you can write maybe B suffix X, but no. Yeah, let us write B suffix X. This is happening for every X in U, right? So now you know what you have to do. So this implies U can be written as union of Bx, right? X in U, where this Bx belongs to script Bx, which is contained in what? Script B. Why? Because script B was union of all such B suffix X, script B suffix X, right? So what it means, guys? See, by definition, so this implies B is a basis for tau on X. So you see, what we have done here, what we have done here. So let me add it as a remark. Remark. From neighborhood basis, we constructed a basis for topology X. Oh, sorry, topology tau on X. Right? Now, let me uh, this is pink color, okay? Pink color discussion above. Let us continue. Okay. Now what I'm gonna do is let script B be a basis for X dot for this topological space X dot. Now let us define something. Define B suffix X to be all B in script B such that X belongs to B. So I have a basis now. What I am doing? I am collecting all sets in that basis, okay, which contain the point X. So define this for X in X. What should be my claim, guys? My claim is script BX is a neighborhood basis for X in X, for the point X in X, right? Let us see why it is true. Number one, clearly X belongs to B for every B in script BX. That is by definition. Number two, since B is open and X belongs to B for every B in script BX, what it implies, guys? This implies B belongs to collection of all neighborhoods of X. That was the second condition. Let me go up if you don't remember it. So this was a second condition. Okay. And now let us come to the third one. Let us prove third one. So let us take for third, let U belongs to NX be arbitrary. So it's a neighborhood. So this implies there exists open set, say V in X such that X belongs to V, which is contained in U. Now, V is open, right? And script B is a basis for what? X. So what will happen, guys? So there exists, this implies there exists B in script B such that X belongs to this script B, which is contained in V, right? Why? By equivalent definition of basis. We have used this many times. So note that this B is in script B. Now, this implies B is also in script BX and B is contained in V, which is contained in U. So see what you have. You started with an open set, oh sorry, a neighborhood. You produced a member here, but where this member is in B suffix X. And then you are claiming that this is contained in U. So for every neighborhood, you have a member of the script BX which is contained in it, in that neighborhood, right? See, that is what the third property is. For every neighborhood, for every U in NX, there is something inside B suffix X which is contained in U. So, okay. So what this implies? So by first, second, and third, what we get? B suffix X is a neighborhood basis for X in X, or other languages at X, small x in X. So you can use both for or at. Okay, so I hope you get it. So what is the remark here? The remark, from basis, for topology. We constructed what? Neighborhood basis or local basis for points in X, right? So you see these two remarks. Let us say this is 1. So from neighborhood basis of each point, we have constructed a basis. And here, say this is 2nd. From basis, we have constructed the neighborhood basis. So you see, 1 and 2 are like we are going from a global concept, from a global concept, which was basis for topology, to local, and from local to global. So you see why we are calling it neighborhood basis, because those neighborhood bases are actually helping me to construct the basis of the space. And why this is local word is used here, because from the bases you can get these neighborhood bases. I hope uh, this lecture is clear to you guys. Just a minute. Yeah. So this lecture is clear to you guys, and yes, let me just, okay, I haven't given you any example of neighborhood basis. Just one example I have given you, trivial one. So I will leave more examples of neighborhood basis, for some other day, for discussion of some concept called first countability. So I will stop here. Thank you for your patience. And in upcoming session, we would be discussing about something called subbases. And after that, we would be seeing many examples of, bases, subbases, or maybe I will give you one or two example of this local basis or local base. Base and base is just, plural singular thing. So whichever you want to use. So I hope this definition is clear. What is a neighborhood basis? These three properties should be there. Initially, I wrote something wrong, but I corrected it. So you see, that is how, you know, we develop mathematics and we understand mathematics. I would have opened book in front of me and just copied the definition, but that's not the right way. How you will learn some things. Like what should happen? Like you may confuse in future, right? That this u should be in b suffix u or b suffix u should be in u. But if you know the logic now, that from basis you have to construct local basis and from the local basis you have to construct the basis, then you will never, actually forgot that. You can always correct it. So by the way, that was a purposeful mistake I have done in order to make you guys learn how to sometimes, correct your own mistakes and how to see, you don't have to cram a definition. Of course, you have to cram it once, but if you forgot some little bit part or you are doing some little bit mistake, you can actually recover it if your concept is clear. So, of course, we have to cram the definitions, but the concept behind the definition or motivation is of utmost importance. So, thank you very much, guys. I hope you like this lecture and the little bit things about mathematics I have told you. That's what you should do. So, thank you very much, guys. Thanks for your attention. Let us see you in next section, next session. Thank you.